Hey students, this is your Professor Emilianchuk, and today I'm going to be talking to you about syntax and semantics. So what we're going to do is further distinguish between structure and meaning, and just by way of review, what we talked about last time is that every argument is made up of assertions, right? So assertions, remember, are true or false, and truth and falsity have to do with meaning. So you should have in your mind, as you prepare for exams and quizzes and things like that, is that semantics has to do with meaning, and meaning in this class at least has to do with truth and falsity. By contrast, syntax, right? Let's apply the concept of syntax to arguments. What we said last time is that for now we're just going to be thinking of arguments this way, is that every argument is made up of at least one premise and exactly one conclusion. And then some of the assertions that we use in our arguments can be represented symbolically. You can come up with a little language, a toy language like CL, which is what we developed in the last class, to successfully represent the arguments, and those that are successful are instances of well-formed formulas, right? So if you're kind of confused by that, don't worry, right? Syntax, though, just has to do with how things are arranged, right? So there's a right way to arrange things and there's a wrong way to arrange things, all right? And we actually came up with some instructions that told us how things should be arranged when we were talking about our language of conditional logic, or CL. And it went like this. It was called a recursive definition. We started out by specifying our alphabetic expressions, and then we specified a rule that allowed us to make the simplest expressions of the language possible. So in this case, it was P and Q. And then we had some variables here, little p and little q, that could stand in for any permissible expression that we could create with the language at all. Then P arrow Q is going to be a permissible expression of the language, and then nothing else is, right? So those that are permissible, that follow the rules of the recursive definition, are well-formed formulas, and so we talked about some examples. Those up there are all examples of well-formed formulas. They all obey the rules. We could also represent modus ponens, the argument form, in conditional logic. This idea that you can say like a conditional statement like if P then Q, P, and therefore Q, you can represent that using the CL language, P arrow Q, P, Q. All right, so when it comes to the midterm, you have to understand that semantics, right, will show up in questions that involve whether a string of symbols is true or false, okay? Questions that involve whether a string of symbols is true or false are semantic questions. Okay, semantic properties are those that have to do with truth and falsity. Okay, so if we're talking about some property, some weird description of a property, and it gets into truth conditions or what makes it true, what makes it false, that has to do with semantics. Right? By contrast, syntactic questions are those that involve the arrangement of the arrangement of symbols. Right? Those are syntactic questions, and syntactic properties are those that have to do with how things are arranged. Okay, so let's get into some new stuff here. Recall that some of the well-formed formulas in CL contain an arrow. All right, so what I'm going to say here is this, is that any well-formed formula of CL that does not contain an arrow is atomic. Otherwise, it's compound. Okay, otherwise it's compound. So P is itself is atomic. It's not attached to anything. It just kind of stands alone, right? Whereas P arrow Q is compound. All right, so that's a distinction you should get to know. We'll be revisiting atomic and compound sentences throughout the semester. Every compound well-formed formula contains at least one subformula. Yes, this is right. All right, so if you see here that P is the subformula of P arrow P, okay? Now with this one, we have P, we have Q, and we have Q arrow P. Do you see that? So there's the P, there's the Q, and then there's the Q arrow P, right? We should also pay attention again to remember what the antecedent and the consequent is. right? The antecedent is this part that's before the arrow. There's the arrow, the main arrow. And then this part's the consequent. And what's going on here when we're evaluating subformulas is that P, the letter P itself, functions as the antecedent for this arrow, but then the consequent for this arrow too, right? Now Q just functions as an antecedent, right? That's the role that it plays in this subformula here, okay? And then this whole thing right here is the consequent of this arrow here. All right, so there's a little game we play here when we kind of determine what is the main arrow. All right, let's think about this. All right, you'll have homework questions that look like this. You'll have some big long string of arrows, and you have to tell me what the atomic components are, and then what the compound components are. So let's go over that. Let me show you how to do that. The atomic components, we have P that shows up in 1, 2, 3, 4, 5 places. And then we have Q, all right? And notice how you only need to note, you don't need to list P 5 times, you just list it once, okay? Because it just, you know, the other ones are redundant. Then you have some other ones. You have P arrow P that shows up twice right there and there. Okay, and then you have P arrow Q. Now you might be thinking, okay, I'm all done, but you're not, all right? You're not, because this arrow here has not been accounted for. We also have this whole thing as a consequent, okay? So notice here that there's 5 subformulas to that particular problem. All right, let's talk a little bit about the main connective. I've been calling it the main arrow so far, but in the same sentence that we were just looking at, you can see the antecedent there is coming before the arrow in white, and then everything in yellow is coming after it, right? That is the main connective, this thing right here, the white arrow, okay? So technically you could say that the main connective is what connects the largest subformulas inside the outermost parentheses. Notice that I have the outermost parentheses in white, so you can kind of see that. All right? Being able to find the main connective is the bread and butter of this course. If you don't know how to do this, you cannot pass. Now, don't worry about this. This is easy. Okay, you just have to train your eye to find the appropriate groupings of the parentheses. Okay? But this is something that's going to affect how we do logic throughout this course till the end. All right, so I want you to get good at this. Okay, so let's define what a syntactic property is formally. I think this is right out of your book. It says a property of an expression or of a collection of expressions in a formal language is syntactic if and only if it depends only on the arrangement of symbols in the formula, okay, and not the meaning. So examples, all right? Here's some examples of a syntactic property. Having an equal number of right and left parentheses. Okay, that has to do with how things are arranged, or only having one sentence letter, or having an odd number of symbols, being a main connective, being a subformula, being crazy long. Okay, these are all syntactic properties. All right. Okay. By contrast, semantic properties. Okay. These determine what a language like CL means. All right. So individual sentence letters represent assertions or singular statements. Right. They can be true or false, and then when they're connected with the arrow, they represent if-then statements. Okay. So CL expresses 2 kinds of assertions. You have your conditionals, those are with the arrow, and then atomic sentences with no arrow. All right, so let's get into the semantics then of if-then statements in CL. All right, this is out of the book. You got to remember this. And I'll go over this in more detail in the coming lectures, so just kind of stick with it. But here it is. A P and Q, and they're little p and q, by the way, be any well-formed formula that you can come up with, then the conditional P arrow Q is false in CL if and only if its antecedent P is true and its consequent is false. Otherwise, it's true in CL. Okay, so you only have one set of circumstances in which these things come out false, and that's when you have a true antecedent, false consequent. Okay, true antecedent, false consequent. True antecedent, false consequent. Okay, get that in your head. That means false conditional. Okay, false conditional. All right, true antecedent, false consequent. Right, in every other circumstance, even if it's a false and a false, or true and a true, or a false and a true, it comes out true. And I'll explain why in further lectures, but just remember, for right now, true antecedent, false consequent equals false conditional. There's different kinds of semantic properties, right? Here's a couple. Logical truths. These are just sentences that or assertions that cannot be false, right? And there's an example, okay? If P, then P, okay? That is a logical truth, okay? And I have a proof. I can prove it, right? So let's assume that the antecedent is true and the consequent is false, right? That's the falsification criteria for an if-then statement in our language. Okay, so if that's the case, then P is true and P is false, right? Because this is true and this is false. That's what what I need to assume in order for this to be false. Okay. However, this is just absurd. Okay, this is a contradiction. P is true and P is false, and so this just cannot be the case. There's no way for me to make the antecedent true and the consequent false, and so therefore it has to be true. It cannot be false, right? Let's think a little bit more about contradictions. Suppose I say that P is true and P is false. Okay, there is no way that what I say there can be true, which is kind of funny, right? Logical falsehoods are those things that cannot be true. All right? Okay. Hopefully that's clear. Sometimes you'll hear it said that if P, then P is a necessary truth or is necessarily true. That's the same thing as saying it's a logical truth, okay? Whereas if P, then Q, suppose we add that one, that's contingently true. That can be true or false, all right? That can be contingently true. Right. And we have some special ways of talking about that we'll get into later on in this class, but just be aware that sometimes logicians talk this way. All right, let's talk about syntax and semantics together in a special piece of notation that you'll need to understand for your homework, right? And this is also in the book. You might be been wondering about this, but a formula of CL is going to be called idempotent if it has the form P arrow P. Okay, and now in this case, P has to be numerically identical with itself. Okay, that's confusing. Let me spell it out a different way. What I'm trying to say here is that the antecedent has to be identical with the consequent. That's what an idempotent is, right? The antecedent is identical with the consequent. Okay, so if it has that kind of form, right, then it's idempotent. Okay. Now it's a syntactic property because it's only defined in terms of how things are arranged, right? So examples, Q arrow Q, right? That's an idempotent. Now, why is that special? Why do we care? Well, the thing is that it actually represents logical truths. All idempotents are logically true, all right? They're all logically true. So this is an idempotent, right? Here is the main connective. Here's the antecedent. It's identical with the consequent. Notice too that this thing is composed of idempotents as well, whereas the antecedent of this whole thing is an idempotent and the consequent of this whole thing is an idempotent. All right? Okay, so that's how these two things can get entangled sometimes, is that we might have a special syntactic property we specify because it maps onto certain things that have a semantic property. Now, not all logical truths are idempotents, okay? Not all logical truths are idempotents. That's different from saying that all idempotents are logical truths. Now, here's an example, okay? This is a logical truth, okay? This cannot be false, all right? There's no way to make this, this whole thing have a true antecedent and a false consequent because the consequent cannot be false. It's a logical truth, okay? You see that? Since its consequent is logically true, I cannot make a true antecedent and false consequent. Okay. Here's another one. It's not idempotent. Okay. Here you have again an idempotent and the consequent, but the antecedent is not the same. Remember, you have to have an identical antecedent and consequent for it to be idempotent. Okay, but it is a logical truth because I cannot make a false antecedent here, which is what I would need to make a false conditional. All right. All that to say is this, right? Remember, this is just by way of memory here. The conditional P arrow Q is false in CL if and only if its antecedent is true and its consequent is false, right? Otherwise, the conditional is true. And so I'm just not able to make the consequent false because the consequents are logical truths, right? They're idempotent. Okay. Assertions can be atomic and compound, all right? So by way of review, we said that assertions have truth value. They can either be true or false. We also talked about the relational structure of some assertions like on, all right? And so here's some new information. Assertions can be atomic or compound. An assertion is atomic if and only if it contains no parts to which a truth value could be assigned. Otherwise, it's compound. So if it has parts to which a truth value could be assigned, it's compound, right? Conditionals are compound because if the atomic assertion in the antecedent is true and the atomic assertion in the consequent is false, then taken as a whole, the conditional is false, right? Okay, there's different kinds of atomic assertions. Here's one, the number 5 is odd. So you have the object, which is the number 5, and the predicate is odd. This one you have John loves cheese. Sorry, I had to take a drink of water there. My mouth is getting dry. Here you have two objects. You have John, you have cheese, and then you have a relation called loves, right? John loves cheese. All right, here's another one. Chicago is between New York and LA. Here you have three different objects. You have Chicago, New York, and LA, right? And they are related to one another by the is between and predicate, okay? So we're going to actually make sense of this distinction between objects and predicates in our language. We'll get into this in the next lecture, I think, or maybe that's coming up. Hold on a second, let me check. Nope, it's actually in this one. Sorry. Okay. Sometimes I get confused. Anyway, objects are what we are naming, and properties and relations are what the predicates are being related. So, let's talk about predicates and degrees. All right, the number 5 is odd, is a 1-degree predicate. Okay, because we have one object being related to a predicate. Whereas John loves cheese is a 2-degree predicate because we have two objects being related by the predicate. And then the is between predicate has 3 objects. See the 3 blank spaces? That's a 3-degree predicate. So degree has to do with syntax, right? Now, predicates in order can matter. Let's just kind of think about this a little bit. Here's a sentence. Zeus is identical with Jupiter. Here, the order of the objects as that appears in the sentence isn't going to matter. You could just as well say Jupiter is identical with Zeus, and it's not going to change the truth value of the statement. All right? Contrast that with this sort of sentence. Zeus is the father of Athena. Here, order matters. You cannot just say that Athena is the father of Zeus and have the truth value stay the same. Okay? You're gonna go from saying something true to saying something false if you switch the order around. So order sometimes matters, right? Order is gonna have to do with semantics in this case. All right, so what we're gonna do in this class is we're gonna make sense of the distinction between objects and predicates. All right, and so all the objects that we can name are going to be indicated by lowercase letters A, B, C through M. That's just the way the convention works in this book. I'm not entirely sure why we only get limited to M, but that's the way the rules are, and so that's what we're going to go with. All predicates are indicated by uppercase letters A, B, C through M, and then nothing else indicates a predicate or an object name. Okay, so to represent an atomic assertion, we place a predicate letter in front of the appropriate number of names. So for example, this is capital F lowercase a, right? That's what we're going to do. So that's what that basically says then in English is A is F. Okay, so let's kind of go back to our sentences. The number 5 is odd. All right, so that's how we represent it. Okay. Now, you might be wondering, well, why did you use D, right, for the predicate? Well, the problem here with the is odd predicate is that I can't use O, so I just go one letter over and use the capital D, and then F is for 5. Okay. Let's look at John loves cheese. Here the predicate is L, so we use a capital L, right? And then John loves the cheese, all right? So that's how you would write that out. Here, you use the between predicate as capital B, Chicago is little c, and then E is for New York. Again, I can't use N, which is so sad. So I just kind of move one letter over in the word new, right? That's E, and so that's where I get the little E from. And then the little L stands for LA, all right? And so that's how you would kind of put things into the language that we're going to be using, right? These are atomic assertions, and they can be represented by this notation. All right? You don't necessarily need to know what the English sentence is in order to read out the language. So if you see this, what this is saying is F is D. Now you may not know what F stands for or D stands for, but it does have a translation into our natural language, English, from the notation. Same thing here. You see this, you have no idea what it's standing for, but you can say this. You could say that J bears L to C. And then in this sentence, you could say that C bears B to E and L. All right. So what the moral of the story is here is that the name that's closest to the predicate is functioning as the subject of your sentence, or what the object that's bearing the action, that's doing the action. Okay. Okay. Oh, all right. So that gets us into our logical language of the day, which is just like CL. All right, except we're going to make a little change to it, and that change then is going to change the language to what's called CL star. All right, so let's let our alphabet consist of 2 predicates, just F and G, and 2 names. All right, and then we have our brackets and our operator, right? That's going to be the alphabet we have, okay? And then any predicate followed by a finite number of names, that's what it should say there, but let's just say that, is actually, I think if I remember correctly from the book, it's just a single name, right? It gets confusing because there's different languages that have different rules, and I think I'm remembering now that this has just a single name. That's going to be well-formed, all right? Then let P and Q be any well-formed formula. Then the expression P arrow Q is a well-formed formula, and then nothing else is. All right, so the following are well-formed. We have A as F, okay, we have B as F, arrow A as G, all right, that's well-formed as well. I'm not going to read that one out, but these are not well-formed, right? R, A, because R is not part of the alphabet. Here we're missing brackets, and let's see, yes, that is not well-formed either because we're missing outer brackets. And that's not well-formed because we can't use N. All right. Okay, so that is basically today's lesson. Here's some practice problems you can look at. You can check these out on your own. You can check out the slides. You know, I have some answers that you can check and look out for. Same practice problems here. I think I actually do give you some answers. All right, so just check those out. check your work against them, get a little bit of practice, and if you have any questions, let me know, and I will talk to you later.